Imagine this for a second. You're standing on the platform, right? Waiting for your train. And it's delayed. First, maybe just a few minutes, okay? But then it stretches out, and suddenly you hear that announcement, service suspension. Or, worse, you hear later about a major disruption, maybe even an accident that maybe could have been avoided. It's more than just frustrating, isn't it? It kind of shakes your trust. It throws countless lives off schedule. We rely so much on these massive, really complex machines, these intricate systems, to just work perfectly. But like a top athlete needs constant, really sophisticated checkups. Something as huge and interconnected as a railway network, well, it needs an incredible amount of care and foresight. So the big question we're tackling today is, why do these disruptions happen? And maybe more importantly, how can we get ahead of them? How do we stop just reacting and actually start preventing them? Okay, let's try and unpack this. Today, we're doing a deep dive into what are called railway health monitoring systems. And we're going to focus specifically on a really cutting edge area known as prognostics and health management, or PHM for short. Our mission, really, in this deep dive is to explore how the whole railway industry is shifting its thinking, moving away from just fixing things after they break to actively predicting when they might break and stopping it beforehand. It's a pretty fundamental change.
Yeah, and what's really fascinating here and why this stuff matters, I think, is that it's not just about, super technical jargon that only engineers understand. This is about real-world impact. It's about radically improving safety, which is huge, obviously, for passengers, for the operators themselves. It's about boosting efficiency in an industry that, let's face it, underpins a lot of our economy. And it's about making the whole experience better for everyone who uses trains. So whether you're, say, an engineering student thinking about the future, or maybe you're just starting your career in this area, or even if you just rely on public transport, this deep dive is for you. We're going to trace the whole journey from sort of old school, often pretty wasteful maintenance methods, right up to today's really smart data-driven systems. We'll get into the details of the data, how it's gathered, how it's crunched to find insights, and ultimately how it all comes together to keep those tracks clear, keep the trains running on time, and most importantly, make sure everyone gets where they're going safely.
That's a great overview. And to really get where we are now, maybe we should just step back a bit. Look at how maintenance itself has evolved over time. Think about, I don't know, the good old days, maybe before, say, the 1950s. Maintenance back then was mostly what you'd call corrective. The philosophy was pretty straightforward, maybe a bit blunt. If it ain't broke, don't fix it, right? So equipment just ran until inevitably it failed, and then you'd fix it or replace it. Seems simple, maybe, but the impact? Really disruptive. Imagine a locomotive just grinding to a halt miles from anywhere, or a critical signal failing without warning. It wasn't just inconvenient, it was expensive, time-consuming, and frankly, often pretty dangerous. There's actually a formal definition, isn't there? Like from the IEC standards.
Yeah, exactly. IEC 6300-314 defines maintenance as the combination of all technical and administrative actions intended to retain an item in, or restore it to, a state in which it can perform a required function. And in those early days, that restoration part, it almost always happened after the failure. Reactive, basically.
Right. And that just couldn't last, could it? Especially as machines got way more complex.
No, precisely. It became a huge bottleneck. As industrial stuff got bigger and more complicated, the consequences of unexpected failures just ballooned. Reacting after something broke down, it just wasn't viable anymore. Not economically, not safely.
Yeah.
So roughly between, say, 1950 and 1980, we saw this shift towards the second generation, scheduled maintenance. Things like systematic overhauls. This meant doing maintenance at set times, maybe every 6 months or after so many miles, or operating hours.
Okay, so that sounds like an improvement. Trying to get ahead of the failures.
It definitely was an improvement, yeah. It aimed to prevent failures by replacing parts proactively, but it had its own problems. You often ended up replacing components that were actually perfectly fine just because the schedule said, time's up. So that meant a lot of wasted parts, wasted labor, and unnecessary downtime for equipment that could have kept running.
Ah, okay. And this is where things start getting really interesting, right? There was this big shift, I think, related to aviation.
Oh, absolutely. The Boeing 747 story in the 1960s. That's kind of legendary in maintenance circles. It was this incredible piece of engineering, the 747. But its complexity was just off the charts for traditional maintenance thinking. Initial estimates for keeping it running were, oh, well, they were staggering. They figured for every 1 hour of flight, It would need 4 hours of maintenance.
4 hours for every 1 hour. Wow, that sounds impossible.
It basically was. It
Yeah.
just defied common sense. It made the plane economically unviable before it even really got going. Think about the cost, the logistics. It would have grounded the whole project. It wasn't just a money problem. It showed a fundamental flaw in the maintenance philosophy itself.
So what happened? How did they solve that?
Well, it was a real watershed moment, particularly for reliability engineering. The FAA, the U.S. Aviation Authority, set up a task force back in 1960, and what they found was actually quite counterintuitive. They discovered that those scheduled overhauls, they had very little impact on the overall reliability of complex systems. Unless the system had one single dominant failure mode that you could reliably predict based on age or usage.
So for many parts, tearing them down on a schedule wasn't helping.
Exactly. For lots of components, fixed schedules weren't effective, and sometimes they could even cause failures by messing with things unnecessarily. This whole realization led to something called the Maintenance Steering Group, or MSG methodology, and that, in turn, led to Reliability-Centered Maintenance, RCM, in 1978.
RCM, okay, I've heard that term. What did it change?
It totally revolutionized the approach. RCM focuses on maintaining the function of the system, not just replacing individual parts. And it determines what maintenance you need based on the consequences if a function fails. It really forced this critical question, which is still super relevant for railways today. How do we get beyond these often wasteful fixed schedules and move to maintenance that's truly intelligent, that reflects the actual real-time condition of each specific piece of equipment?
And that leads us naturally to condition-based maintenance, CBM, right? Which started gaining ground in the 80s.
Precisely. With CBM, you ditch the rigid calendar. You only do maintenance when the asset's condition actually shows it's needed. This is often based on, regular checks, inspections, or even better, continuous real-time monitoring using sensors.
You mentioned the PF curve before. Can you explain that a bit?
Sure. Think of it like a graph showing how a fault develops over time. P is a point where potential failure is first detectable through monitoring. F is the point of functional failure, where the thing actually stops working properly if you don't do anything. CBM tries to catch the problem and intervene somewhere in that PF interval, that window between detection and failure.
Okay, so it's using that early warning sign to act before it breaks down completely.
Exactly. It's about listening to the machine, letting it tell you when it needs attention, rather than just looking at the clock or the mileage.
And then predictive maintenance takes that even further.
Yeah, predictive maintenance is really a more advanced, sophisticated form of CBM. It
Yeah.
doesn't just tell you that a failure is likely coming. It uses more advanced analytics, statistical models, machine learning, that kind of thing, to forecast when it's likely to happen. And that key prediction is what we call the remaining useful life, or RUL.
RUL, remaining useful life. That sounds incredibly powerful.
It really is transformative. If you can accurately estimate the RUL, you can time your maintenance perfectly. You maximize the use you get out of the asset, you use your resources efficiently, and you minimize disruption because you can plan the maintenance for the least disruptive time.
And what made all this possible, especially since the early 2000s, things seem to have accelerated?
It was really a perfect storm, a convergence of technologies.
Okay, like what?
Well, first, you had the explosion of low-cost, pretty robust wireless sensors and the whole Internet of Things, the IoT, taking off. Suddenly, getting detailed data from almost anything, anywhere, became practical and affordable.
Right, sensors everywhere.
Second, massive leaks in computing power applied to statistics and especially machine intelligence, AI, and machine learning. These algorithms got really good at finding subtle patterns in huge amounts of data.
And the data itself, managing all that.
That's the third piece. The ability to actually manage, store, and process these enormous big data streams affordably finally caught up. Think cloud computing, parallel processing. So you had the sensing, the smart analysis, and the scalable data infrastructure all coming together. That really created the foundation for PHM to flourish.
So bringing it all together then, prognostics and health management, PHM, it's the culmination of this whole evolution in maintenance thinking.
Exactly. PHM basically encompasses all the methods, the tools, both hardware and software that you use to perform diagnostics, assess the health, and predict the future of industrial assets. It's really holistic. It's not just reacting, it's detecting those very first hints of trouble, those incipient faults. Then it's about isolating them, figuring out the root cause, and the really powerful part, predicting that remaining useful life, the RUL.
But it's more than just prediction, you're saying.
Absolutely. The ultimate goal is to support better decisions about maintenance and logistics. It means considering everything:
Hmm.
resource availability, how the asset is actually being used right now, the economic consequences of different actions. It allows managers to move from, frantic reactive repairs to strategic data-driven planning.
So for railways, with all their complexity, what does this PHM approach actually mean for their big goals, like keeping things running smoothly and safely?
That's the key question, right? Its purpose goes way beyond just fixing broken parts. PHM creates this vital link with RAM.
RAM reliability, availability, and maintainability.
Okay, yeah. Traditionally, those are often looked at separately in engineering. But integrating them, which PHM helps enable, offers huge potential for improvement across the whole system.
Why is that integration so important for railways specifically?
Well, think about traditional reliability analysis. It often looks at historical data, averages for the whole fleet, like the average performance of a certain type of wheel set. And that's great for high-level planning for understanding general trends, but it doesn't tell you much about the unique condition of one specific wheel set on this particular train operating under these specific conditions right now.
Ah, so it's the difference between the fleet average and the individual reality.
Exactly. One wheel set might be running hotter or under more stress than another identical one on a different train or route. PHM captures those individual differences. It shifts the focus from the fleet average to the individual component's health state, right here, right now.
Yeah.
And these two views, the fleet level reliability and the individual PHM view, they aren't opposed. They actually complement each other perfectly. You get the big picture and the detailed diagnosis.
Okay, so how does PHM specifically impact reliability? Does it make the parts themselves stronger?
That's a great clarification. No, PHM doesn't inherently improve the design reliability. You can't monitor a poorly designed part into being the better part. But what it does do is help you avoid the operational consequences of a fault by catching problems early before they cause a full failure. PHM preserves and extends the operational reliability. It keeps the asset doing its job without those unexpected breakdowns. It turns potential failures into manageable, planned maintenance.
Got it. And that naturally impacts availability, I assume.
Directly. If you prevent unexpected failures, you massively increase uptime. PHM reduces how often those disruptive failures happen. It also speeds up fault finding if something does go wrong, because you often have a better idea of what the issue is, and it boosts maintenance preparedness. Imagine knowing exactly which part is degrading, how fast, and roughly when it needs attention. You
Yeah.
can have the right spares ready, the right team scheduled. It minimizes downtime.
Makes sense. And maintainability, how does it help there?
By providing those precise, real-time insights, it makes the maintenance itself easier and more effective. Teams can shift from doing broad, generic inspections to highly targeted interventions. They can do less invasive work or more efficient repairs exactly when and where needed. It optimizes the whole maintenance process.
So PHM benefits from RAM thinking, but it sounds like RAM engineering also helps build better PHM systems.
Absolutely, it's a two-way street. RAM engineering provides powerful tools for designing and implementing PHM. Take something like failure modes and effects analysis, FMEA. That's crucial.
FMEA, right? That's where you systematically map out everything that could possibly go wrong.
Exactly. You identify potential failure modes for a component or system, understand their causes, and critically assess their potential effects, especially the ones that cause service-affecting failures, or SAFs. By doing FANAs, railway engineers can pinpoint which assets are most likely to cause major problems if they fail. And just as importantly, it helps identify what physical variables you need to monitor to get the earliest warning of those specific failure modes.
So the FMEA tells you where to put your sensors, essentially, what signals to look for.
Pretty much, yeah. If an FMEA shows, say, bearing overheating is a critical and common failure mode for a certain bogie type, then temperature sensors and vibration analysis immediately become high priorities for your PHM system. It gives you a focused monitoring strategy.
Okay. Now, with something this potentially transformative, especially in a safety-critical industry like rail, I imagine standards become really important.
Oh, absolutely vital. You need standards for interoperability, making sure different systems can talk to each other. You need common approaches so everyone's applying PHM effectively. And you need standards to build trust in these advanced systems. Organizations like the European Railway Agency or the UK's Rail Safety and Standards Board, they're working hard on common technical standards for railways overall. And while a single, perfect railway-specific PHM standard is still kind of evolving, we rely on some important general ones. IO's 19359 gives general guidelines for condition monitoring and diagnostics with nods to prognostics. And there's also iOS-E P1856, which is a dedicated PHM standard that's gaining traction. It sets out a really useful framework.
And these standards, they outline the core steps or phases involved in PHM.
Yes, exactly. Both ISO 1CD359 and P1856 describe a series of fundamental capabilities. You can think of them as phases that are essential for any effective PHM process. It's like a logical flow from raw data to action.
Okay, walk us through those phases. What's step one?
Step one is data acquisition. This is all about getting the right data. But it's way more than just sticking sensors on things. You have to strategically figure out what needs monitoring the critical elements. These are usually the things that fail often or cause really severe disruptions or take ages to fix or are just super expensive to replace.
And that's tricky for railways, right? With tracks and
It's a
trackage.
unique challenge, yeah. You've got static infrastructure tracks, signals, overhead lines stretching for miles, and you've got dynamic moving assets, the trains themselves. Getting good, coherent data from both requires a really coordinated, integrated platform.
Okay, so you've acquired the data. What's next?
Phase two is data processing. Raw sensor data is rarely ready for analysis straight away. It's often noisy or in the wrong format. So this step involves cleaning it up, filtering out noise, maybe transforming it like converting vibration signals into frequency spectra to see hidden patterns. You're basically extracting the useful information.
Got it. Make the data usable.
Then comes phase three, detection. This is like the initial alarm bell. Algorithms analyze the processed data to see if the system's behavior shows any signs of starting to degrade. You're looking for those first subtle clues that something's changing, deviating from normal long before it actually fails. Early warning, essentially. If something's detected, it triggers the next steps.
And the next step is diagnostics. How's that different from just detection?
Good question. Detection just says something might be wrong. Phase four, diagnostics, digs deeper. It analyzes the detected anomaly to figure out exactly where the problem is, how severe it is, and crucially, what's causing it, the root cause. Think of it like a doctor diagnosing an illness versus just noticing a symptom. This detailed information is what really separates PHM from basic condition monitoring.
Okay, so now you know what's wrong, where, and why. What's phase five?
Phase five is the big one, prognostics. This is the prediction part. It's all about estimating that remaining useful life, the RUL, of the component or system. This is often the most challenging phase, but it delivers huge value. By calculating the RUL, ideally with some kind of confidence level, you can figure out the absolute optimal time to intervene with maintenance, maximize asset use, minimize impact on operations. It's about precise timing.
And the final piece?
The sixth and final phase is advisory generation, sometimes called health management. This is where everything comes together. All the information gathered, processed, detected, diagnosed, prognosed, it's synthesized into actionable intelligence. This intelligence is then presented to the decision makers, maybe through dashboards, visualizations, or fed directly into maintenance planning systems. It's about turning insights into informed actions.
Those 6 steps sound logical, but I bet putting them into practice on a real railway is where the scariest challenges lie.
You bet. It's one thing on paper, quite another in the real world.
So practically speaking, what are the big hurdles? You mentioned data quality earlier.
Yeah, that old saying, garbage in, garbage out. It's absolutely fundamental to PHM. The best algorithms are useless if the input data is flawed. So the reliability of the whole acquisition chain, the sensors, the loggers, the communication links, it has to be rock solid. You need good noise filtering, proper calibration. And the frequency you collect data at, the sampling rate, has to be right for the specific problem you're tracking.
Like, tracking a fast-developing crack needs faster sampling than slow track wear.
Exactly. You have to tailor the acquisition to the physics of the degradation process you're monitoring.
Okay. And if you're investing all this effort, how do you actually measure if the PHM system is working? How do you know it's successful?
That's where KPIs come in, key performance indicators. They're essential. They quantify success, justify the investment, and also pinpoint where you might need to improve the system. For PHM, we typically define 6 types of KPIs, and they map directly onto those 6 phases we just discussed.
Can you give us a flavor of those? Maybe highlight a couple of the really critical ones for railways?
Sure. Let's maybe focus on 2 key areas. First, the prognostics KPIs. These measure how well your system predicts that remaining useful life, the RUL, this is kind of the holy grail for railways, right? Knowing when something will fail, not just if. So researchers focus on metrics that assess, for example, the precision of the RUL prediction, how tight are the confidence bounds, and how stable is that prediction over time. You don't want it jumping around wildly. We also use things like the ARC criterion to quantify the uncertainty and ensure the prediction meets certain accuracy requirements. Basically, how sure are we about this prediction?
Okay, so measuring the quality of the prediction itself. What's another key area?
The other really critical ones are the advisory generation KPIs. These measure how well the entire predictive maintenance process actually performs in the real world. This is the bottom line. Success here is measured by direct operational impact. Are you seeing a measurable drop in those service-affecting failures, the SAFs? Is overall service availability going up? Ultimately, these KPIs feed into the cost-benefit analysis. Does the PHM system actually save money by avoiding failures, reducing maintenance, preventing fines? That's what these KPIs help demonstrate.
Right, proving the value. And the other KPIs for data acquisition, processing, detection, diagnostics, they all feed into making these final ones accurate.
Exactly. They ensure the whole chain, from sensor to decision, is robust and reliable. Each step has to work well for the final outcome to be effective.
Okay, so let's talk about getting this stuff out of the lab and onto the actual tracks and trains. You mentioned challenges. What kind of hurdles are we talking about, starting with the hardware?
Right, this is where theory hits reality hard. First off, compliance. Railway standards are incredibly strict: electromagnetics, vibration, temperature, you name it. Does the new sensor system meet all those standards? If not, you might have to reopen the entire safety case for the train or track section it's on. That means huge costs, delays, tons of retesting. It's a massive hurdle.
And just physically installing it.
That's the intrusivity issue. If adding a sensor significantly changes the thing it's monitoring, its structure, how it behaves, then you're back to needing serious safety reevaluations. You can't just bolt things on without thinking about the impact.
And finding space and power, especially on a train.
Exactly. Processing and storage. Labs have infinite resources, practically. A bogie on a moving train. Space is tight. Power is limited. The environment is harsh. Does the PHM system need its own dedicated hardened computer on board? Can it use existing systems? These physical constraints drive a lot of design decisions.
What about getting the data off the train or from the trackside?
Communication networks. This is huge. A full PHM system generates vastly more data than typical remote diagnostics. Existing 4G routers on trains often can't handle that volume. So do you need a dedicated high-speed link, maybe Wi-Fi or Ethernet, that dumps data automatically at depots?
And the monitoring system itself needs to be reliable. Kind of ironic.
Very much so.
Right.
Reliability of the PHM hardware. If your sensors, wires, processors keep failing, they just become another maintenance headache. They add cost and workload. And eventually people might just say, this PHM thing is more trouble than it's worth, and switch it off. The system itself has to be dependable.
Okay, so those are the hardware headaches. What about the software side? Integration there.
Equally complex. First, bandwidth constraints. We touched on communication networks. If you can't get enough bandwidth to send all the raw sensor data, you might be forced to do some processing on board the train, like feature extraction, distilling complex raw signals down to simpler, meaningful indicators. You then only send those features off board. Ideally, you want the raw data for maximum flexibility later, but it's often a necessary trade-off.
And safety, if these algorithms start influencing things.
Critical point. Safety integrity levels,
Yeah.
SILs. If a PHM algorithm's output could affect a safety-critical function, maybe trigger a brake application or a speed restriction, it has to meet incredibly rigorous SIL requirements. This dictates everything from the programming languages used to the exhaustive testing and validation needed. It's a very high bar.
And just handling the sheer volume of data from a whole fleet.
IT architecture scalability. Yeah, imagine hundreds of trains, thousands of miles of track, all sending data constantly. It's an enormous amount.
Yeah.
Your IT backend has to be built for this scale, usually using cloud platforms, infrastructure as a service, platform as a service designed to grow without constant hardware upgrades. You also need to think about global IT availability. Is the system always up and running when the maintenance teams need it? What's the service level agreement, the SLA?
And finally, how do people actually use all this information? The interface.
The human-machine interface, HMI. This is so crucial, maybe the emerging part of the iceberg, because the smartest system is useless if people can't understand or act on its output. The HMI needs to be intuitive, clear, easy to use, reliable. What does it absolutely have to show? Usually, the current health status, the type of problem detected, some kind of health index or score, and that critical RUL prediction. And ideally, it lets users see historical trends, track how things are changing over time. It's got to empower the user, not overwhelm them.
Wow. So many interconnected challenges, but you're saying tackling them is worth it because the stakes are just so high in rail.
Absolutely. It
Yeah.
brings us back to the why bother. PHM isn't just a nice to have, it's becoming non-negotiable for railways. There are two massive drivers pushing this, beyond just the cost of traditional maintenance. First, those scheduled overhauls are incredibly expensive, and as we saw with the 7-Ford season, often unnecessary. Wasted money, basically. Second, and much more critical, is the huge impact when things do fail. We're talking massive, costly delays that affect millions, disrupt freights, and tragically, failures can lead to severe accidents. The safety implications are enormous.
And the demand on railways is only increasing, right?
Massively. Projections showed European passenger and freight traffic potentially doubling or tripling by 2020. You can't just keep building endless new tracks to meet that demand. It's too expensive, too slow, too disruptive environmentally. The only way forward is to make the existing networks fundamentally safer, more reliable, more efficient.
And PHM is the key enabler for that.
It's a huge part of the solution. Because the core benefit is that early identification of problems before they cause failure. That directly translates to higher availability, more trains running reliably, enhanced safety, and significantly lower maintenance costs through targeted, proactive work. It's about managing risk intelligently.
Okay, let's make this more concrete. Can you give us some examples? Where is PHM really being applied in railways today? Let's start with turnouts. What are they and why do they matter so much?
Sure. Turnouts, sometimes called points or switches, are basically the junctions on the railway. They're mechanical devices, usually with a motor, that move sections of rail to guide a train from one track to another. They're absolutely essential for traffic flow. Without them working properly, you can't route trains effectively across a network.
And when they fail, it's bad news.
Catastrophic for operations. A faulty turnout basically stops traffic in its tracks or forces lengthy, slow reroutes. The delays are massive. Just look at the numbers. UK's Network Rail reported something like 433,000 minutes of passenger delays in 2014 just from turnout failures.
Wow, nearly 500,000 minutes.
Yeah. And in Germany, Dibon estimated turnouts caused 19% of all delay minutes back in 2010. That's around 28 million minutes. The knock-on effects are huge.
And it's not just inconvenience, there are real financial penalties too.
Absolutely. Network operators get hit with big fines if they miss performance targets. Network Rail, again, was fined over £50 million in 2015 for missing targets, partly due to reliability issues like turnouts. They then had to spend an extra $25 million specifically to improve things. So any improvement in turnout reliability is direct savings plus better service.
What typically goes wrong with them, and what about safety?
Common issues are things like wear on critical moving parts, small misalignments that build up over time, lack of proper lubrication causing friction and stress. Traditional maintenance involves lots of adjustments. Lubrication is costly. In the UK, maybe $3.4 million a year just for point machines on 1,000 kilometers of track. But the safety aspect is paramount. The Potter's Bar accident in the UK back in 2001 was a terrible reminder. Poor turnout maintenance was a key factor in that fatal derailment. It really underscores why proactive care is vital.
So how does PHM help with turnouts?
Research is heavily focused on detecting those incipient faults, the very early signs of wear or misalignment. For example, Alstom did tests back in 2015 using a test rig. They simulated different defects over thousands of cycles while monitoring lots of signals, motor current, vibration, position. Then they used an artificial neural network, an ANN, to analyze that data, calculate a real-time health score for the turnout, and predict its RUL based on how the degradation was progressing.
So predicting failure before it happens, allowing intervention.
Exactly. PHM makes it possible to see how the turnout is degrading and step in at the best possible time. Saves money, prevents massive delays, and crucially, improves safety.
Okay, another critical area, bogies. You mentioned these earlier. They're more than just wheels, right?
Oh, much more. A bogie is a really complex subsystem. It's the whole assembly underneath the rail car that holds the wheels and axles. It includes the suspension systems for ride comfort, often parts of the traction system like motors and gearboxes, the critical axle bearings, brakes, plus lots of electronics and sensors. It's what connects the car body to the wheels and handles all the forces.
And they're expensive to maintain and critical for operation.
Hugely expensive, yeah. Bogie maintenance is complex and time-consuming. And if a bogie fails significantly, the train is basically out of action. It has a massive impact on availability. So they're prime candidates for PHM. The goals are usually threefold. Cut down on those service-affecting failures like predicting hot axle box alarms before they trigger trackside detectors. Second, reduce maintenance costs, maybe optimizing when you do expensive wheel set overhauls. And third, increase availability, perhaps automating some visual checks that currently take a lot of manual effort.
What specific kinds of failures or degradation is PHM looking for on bogies?
It depends on the component.
Yeah.
For those hot axle box alarms, it's looking for early signs of bearing problems, fatigue, wear, cracking.
Hmm.
Symptoms might be abnormal vibrations near the bearing,
Mhm.
slight rise in temperature, specific noise patterns, maybe finding tiny metal particles or water in the grease, or changes in grease viscosity.
Okay. And for things like wheels needing overhaul?
There, it's looking for things like shelling or spalling, where bits of metal break off the surface, or the propagation of fatigue cracks within the wheel, or excessive wear from contact with the rail. Symptoms could be visible cracks, an unusual surface condition detected by sensors, or, again, characteristic vibration patterns.
And for the bogie frame itself, automating visual checks.
Yeah, looking for fatigue crack initiation or growth, signs of impact damage, corrosion, or deformation. The symptoms might be tiny cracks, impact marks, or again, abnormal vibrations picked up on the bogie or even transmitted to the car body.
And how do you get all this information? What sensors are used?
A whole range of sensors get deployed. Temperature probes near bearings, obviously. Accelerometers are key for vibration analysis. Displacement sensors to check suspension movement. Viscosity sensors for lubricants. Strain gauges to measure stress on frames. Maybe piezoelectric sensors for force measurements. It's a diverse toolkit, providing that raw data stream.
Right. Let's widen the view again. Railway infrastructure, tracks, signals, power lines. That seems like a huge challenge for monitoring.
It's immense. You're talking about assets spread over vast distances, signaling, electrification like overhead lines, the track itself, the ballast underneath, bridges, tunnels. Maintaining all this is incredibly labor-intensive, costs a fortune, and needs incredibly complex coordination with train schedules. It's a massive operational puzzle.
So where does PHM fit into infrastructure management?
It's absolutely crucial for hitting those goals of high availability, safety, and lower costs. But it's challenging. You have to adapt PHM techniques originally designed for contained mechanical systems like a gearbox to this huge distributed network. Research often focuses on key areas like track health and the overhead contact system, the OCS or catenary.
Okay, track health. What kinds of problems are monitored there?
Broadly, two types. Geometrical defects, these are longer wavelength issues like problems with the track's levelness, its alignment, or the gauge distance between rails. These are often monitored by special measurement trains, and the data gets fed into predictive models, often ANNs, to forecast how the geometry will deteriorate.
And the other, shorter defects.
Right. Short length irregularities. These are things like squats, those dips on the railhead corrugation, or ripples, or internal cracks within the rail. These need different techniques. Ultronic inspection cars use sound waves to find internal flaws. Or you can analyze axle box acceleration, ABA data, often from regular service trains, to detect surface defects like corrugation.
And the overhead power lines, the OCS.
For the OCS, monitoring focuses on a few key things: geometry wire height, stagger, its side-to-side position, and wear on the contact wire itself. Mechanical aspects like the force between the train's pantograph and the wire, which needs to be stable for good current collection, and electrical factors like the rate of arcing, which signals poor contact. Techniques here include using high-speed cameras on trains to check things like dropper positions, and using models heuristic or ANN-based to predict contact wire wear so it can be replaced proactively.
It sounds like for infrastructure, getting enough failure data might be hard. Things last a long time, hopefully.
That's a key challenge. Run-to-failure data is often sparse for infrastructure. Components last decades, the scale is huge. So PHM for infrastructure often relies heavily on hybrid approaches. These cleverly combine physics-based models which understand material behavior with data-driven insights from whatever monitoring data you do have. And crucially, these models often use data from both those dedicated inspection trains and data collected from sensors on regular passenger and freight trains as they run their normal routes. Combining sources gives a much richer picture.
These examples really show the potential, but also hint at the complex technology running underneath it all. Let's talk about the IT side.
Yeah, this is where it gets really interesting, the stuff behind the scenes. Beyond the sensors and algorithms, the IT infrastructure is the absolute foundation.
What are the key IT challenges?
Well, things like ensuring algorithms can run parts of their calculations in parallel, just for speed. Optimizing how you structure the databases to handle and quickly query massive amounts of raw data. Deciding between decentralized processing, doing calculations near the asset, versus a centralized approach where all data goes to one place. Each has pros and cons for railways.
And just keeping up with the data growth.
Scalability, it's paramount. The system has to grow easily as you add more sensors, more trains. This usually points towards cloud solutions, IaaS, PaaS, SaaS models. Then there's cloud versus on-premises storage and processing, proprietary versus open-source software choices. How you optimize the software architecture itself, maybe using something like a Lambda architecture to handle both real-time and batch processing efficiently.
And security must be a massive concern.
Oh, huge. Cybersecurity. Protecting this vast, critical network infrastructure and all the sensitive operational data it holds is an enormous ongoing challenge. Railways are critical infrastructure, making them targets.
So looking ahead, what are the big frontiers, the remaining challenges for PHM and rail?
There are several exciting frontiers. One is refining those hybrid algorithms, getting even better at blending data-driven insights, physics models, and expert knowledge. That's key for complex systems. Another is pushing decentralization further, getting more intelligence closer to the assets to reduce the need to send massive raw data streams centrally. And then there's the move towards true fleet-based PHM, going beyond monitoring individual assets to making optimized maintenance and operational decisions across the entire fleet or network. That's a really complex optimization problem.
And are there lessons or technologies coming from other fields?
Definitely. There's huge potential in leveraging progress elsewhere. From data science, combining unsupervised methods like clustering to find unknown patterns with supervised classification. From deep learning, using those multi-layer neural networks for automatic feature discovery and pattern recognition in really noisy data. Integrating more closely with traditional reliability engineering, linking reliability models like Cox proportional hazards directly to monitored stresses. And with traditional maintenance engineering to better model and optimize maintenance effectiveness itself, it's about connecting the disciplines.
So what's the ultimate vision here, if PHM really delivers on its promise for railways?
The aspirational future, the big goal, is aiming for near-zero service-affecting failure rates. Imagine a railway where unexpected breakdowns are almost unheard of. It's about drastically reduced maintenance costs through highly optimized condition-driven work and achieving dynamic balancing of maintenance load in depots, optimizing resource use across the whole network.
So it's not just small improvements, it's a completely new level of performance.
Exactly. It's ushering in a whole new era in a railway system, reliability, availability, and life cycle cost optimization. A fundamental shift.
Are there still big open questions or opportunities being explored right now?
Oh, absolutely. A big area is making better use of all the condition monitoring data that already exists, especially data coming from regular revenue service trains, not just special inspection vehicles. The challenge and opportunity is effectively combining information from all these different sources, especially the non-dedicated ones, to get a richer, more timely picture. There's also a growing push for a design-to-PHM mindset, building PHM considerations right into the initial design of new trains and infrastructure, not adding it later. Regulatory frameworks also need to evolve to handle PHM-driven maintenance decisions, especially for safety-critical parts, replacing traditional time-based schedules. That requires new thinking on certification.
And future research directions.
Lots of exciting stuff. Developing better canary devices, cheap sensors designed to fail early as a warning. Improving methods to transfer fault knowledge between similar assets in a fleet, and maybe the most futuristic, developing proactive RUL control systems. Systems that don't just predict remaining life, but actively adjust operating parameters, maybe speed, load to actually extend the life of a component, within safe operational limits, of course. That's moving from prediction to control.
Wow. What an incredible journey we've covered today, from, just fixing things when they broke to building these incredibly complex intelligent systems that aim to predict and even prevent failures entirely. It really shows the power of data, of advanced analytics, when you apply it to something as vital as our railway networks. I mean, safer, more reliable, more efficient journeys for all of us.
It really does. And maybe this raises a final thought, something for you, our listeners, to consider. Given this amazing progress in PHM, and this vision of almost eliminating unexpected failures, how might the role of the railway engineer or the technician, or even your own experience as a passenger, how might that change in a truly prognostic railway system? Where failures are preempted rather than just fixed? What new skills, what new ways of thinking will be most valuable in that kind of data-rich future? And what part might you play in shaping this really exciting evolution in railway safety and innovation?